Okay, before I get started with the lecture, I want to talk a little bit about lab because you can save some time by doing one thing before coming to lab. So what we're going to be doing in lab is we're going to be trying to identify materials by how they react when we put different stuff in them. Yay. So what you're going to have is these household chemicals. You won't know which one's which. They're just labeled 1 through 9. And then you have those reagents, the tincture of iodine, phenolphthalein, white vinegar, isopropyl alcohol, and sodium hydroxide. And you're going to mix them and see what happens. And you have a table here that shows you what the reaction should be if you mix the different tests.
Are we supposed to copy that?
So, no, it's in your lab guide.
Okay.
But what you need to do is based on this table. So based on this table, create a test plan. That is, what test do you want to do first to try to make the fewest number of tests possible to identify each one of your materials?
Wait, can you say that again?
You want to figure out which test you want to do first, which one you'll do after that, and so on, to make the least number of total tests to figure out which material is which. So, for instance, the first thing you want to do is something that will separate as many as possible. All of them are basically giving us 2 separations. And a sample beginning is shown right here. So the first test that you're going to want to do is see if it's soluble in water. So your test diagram should start like this. You have unknowns A, B, C, D, E, F, G, H. Well, 1 through 9 is what we have. And then water. And then if it's soluble, put in a box which things you have, possibilities. If it's not soluble, which things you have as possibilities.
How are we going to know?
From this table. So water solubility, the test number 1, the tests are all described right here. So test number 1, water solubility.
So
These up here.
This was one of my more favorite labs.
See this? These are insoluble. So if it's insoluble, you know you have cornstarch, white chalk, or parrot plaster Paris. If it's soluble, then you have one of these.
So we're just going through it first and saying if we think it's soluble or not?
Well, the first test you're going to do is to see if it's soluble in water. And then you'll have it split out to either it's one of these 3 or one of these 6. Is that 6? 2, 4, 6. Yeah.
You're basically trying to figure out what you have by testing it on these different tests.
Well, yeah, I understand that, but my question is we're doing this in lab, not before lab?
Well, coming up with your test plan, do before lab. And then in lab, you're going to follow that plan. So you're going to take sample 1 and you're going to do test 1. And if it's soluble, then you're going to do whatever you decided was test number 2.
So
If it's insoluble, you'll do whatever you decide here was test number 3. Those are not corresponding to the numbers here. They're the tests that you choose to do to try to differentiate. So just following on one side, since there's only 3 that are insoluble, let's say after the first test you find that it's insoluble. You have only 2 other tests that would be appropriate for insoluble. What are the 2 tests that would be appropriate for insoluble? You have iodine and vinegar. So the next one you're going to choose will either be iodine or vinegar. And notice iodine gives you 1 positive and 2 negative. Vinegar gives you 2 negative and 1 positive. So which one should you do next? In this case, it doesn't matter because both of them are going to give you 2 one way, 1 the other. So the order for the next 2 tests, if it was insoluble, it doesn't matter. You do this one, then this one, or this one, then this one. And if you do, let's say you do the iodine test first, if it's positive for the iodine test, then you know it's cornstarch. If it's negative, then you do this test. And if it's positive there, it's white chalk. If it's negative, it's plaster Paris. So you're done with that side. That side's very quick for the insoluble in water. For the soluble in water, if you look at these, this one here is annoying because you have medium pink, light pink, and negative. This one here has a positive there, 2 positives, 4 negatives. This one has 1 positive. This here has slight increase and no effect. Those are, small. And then this one here has soluble, mostly soluble. So the best you're going to do is separating 2 from the rest. And so you choose which test am I going to do second. You're definitely wrong if you chose to do the hydroxide test second because it would only give you 1 possible separation. But the other ones you have choices, and you want to come up with the sequence that you're going to follow to do the minimum number of tests to determine what each material is. So before you come to lab, if you have your plan of attack done, and I want you to put that plan, once you have it all figured out, put it on the back of the page that I just gave you. The front of the page is where you're actually going to put the results of your tests. So make sure you bring that with you to lab tomorrow. So I just want to make sure I cover that now, save us some time in lab tomorrow. You're welcome. All right. 2.
I have 2 more questions.
Are you going to be able to do it? I saw your email this morning.
Yeah, no, class is over.
So Jessica, my brain went blank. Jessica sent me an email indicating that she was ill and wasn't able to work on the homework when she planned on working on it and asked for an extension.
Yeah, and I did one because I've been doing lesson plans and doing other things.
In general, I want to stick with the schedule, but being ill is something that's outside of your control. Like the lesson plans. The lesson plans are assigned and they have to be done. They take time, but they are things that you can plan around, whereas being ill, you can't plan around.
Yeah.
So I will postpone it until Thursday.
Tomorrow?
Yes, tomorrow. Yes, I can still answer questions. What's your question, Jessica?
Number 5, I'm at 8, not 9. I said 9 in the email, but 8.
So I'm going to actually go to so I hate that.
Number 5. Number 8.
It just logged me in with the wrong account. I gotta log out and try to log in with the right account. No, see, it has the right account information. I hit login and then it changed it. Hopefully this logged in right. I thought Jessica just walked out. Really? You want me to work on problems and then you leave? I'll never get logged in. It's the automatic fill that's the problem.
Because 2 of the days that I need to work on it, I have meetings with Adams all day.
Okay. See, now it says, look, you were already logged in all along. It just hates me. I will get to the homework now very quickly. Okay. What? Oh, I looked at 5. I was like, why are the answers there? We need to go to homework 6. All right, I am now with you, Jessica. So which problem am I looking for? Number 5. If matter is made of atoms and atoms are made of subatomic particles, what comes together to create subatomic particles? Where might you find such information? Okay, so this is one that you look up on the internet, right? This isn't one that you have from the textbook. Yeah. So you look up.
Yeah, this is in the textbook.
It is?
Yep, page 303.
Huh. I didn't think it was.
Same.
So, I mean, I can give an answer, but the idea here is for you to, yeah, I thought it was to look it up. I didn't realize he says on page 303. Do you know what atoms are made up of? Okay, protons, neutrons, and electrons. Electrons are fundamental. Protons and neutrons are not. But if you look at the back of the classroom, I have a poster that shows what protons and neutrons are made of.
Yeah.
So, yeah, look it up. Number 8, a radioisotope. Radioisotope means that it is a nucleus that is radioactive. A radioisotope is placed near a radiation detector which registers 80 counts per second. 8 hours later, the detector registers 5 counts per second. Now, we learned about radioactivity, and we learned that the number that remains after one half-life is 1/2, right? Well, the rate at which they decay, that is the number of decays per second, is proportional to how many are present. So if the number of decays per second is cut in half, that means the number of radioactive nuclei you have is also cut in half. So the same rules we learned for half-life with the number of atoms applies to the rate of decay. So in this case, if it goes from 80 counts per second to 5 counts per second, how many times has 80 been cut in half to get to 5?
3, goes to 40, then 20, then 4.
Okay, to 40, then to 20, then to 10, then to 5. So it's 4. So how many half-lives has it been? 4. And since a half-life, does this take? Oh, yeah, okay. So it's done 4 half-lives, and we've gone for 8 hours. So divide by, yeah. That was the outcome.
Oh, I thought you were like asking us the question.
Oh, no.
Out loud.
Any other homework questions? When food is irradiated with gamma rays from a cobalt-60 source, does the food become radioactive? What is a gamma ray? What is a gamma ray? We had alpha, beta, and gamma. What was alpha?
Alpha was the weakness.
Those are the 3 types of radiation. What is alpha?
No charge. Gamma's no charge.
Okay, gamma has no charge and no mass. Gamma is a photon. It's a particle of light. Alpha is 2 protons and 2 neutrons, positive charge. Beta is an electron, negative charge. So this is essentially light. What's the difference in gamma radiation and light? The gamma radiation has a much higher energy than visible light does. So the question is, did it make your food radioactive?
No.
No, what did it do?
It heated it?
Yeah.
Okay, heated is actually correct. It absorbed energy from the photon. And by definition, if you transfer energy with light, that's radiative heating. But the reason they use it is because it will break chemical bonds, which is what makes it dangerous to us. why it can cause cancer can break chemical bonds in your body, and then they can reform wrong. So it's breaking chemical bonds with the goal being to break the bonds in bacteria to denature it. But it's not putting in something that is going to break a nucleus apart, so it's not radioactive. Now, if you put the cobalt-60 in your food, that would make it radioactive. All right. Continuing on then with chapter 14 and getting a start in chapter 15, hopefully. We've used 15 minutes, so probably not. Make sure you are connected to WooClap, because I think I have 3 questions right now on WooClap.
Right away.
Yep.
I'm ready for knowledge. Raise your head, there's no voting in process at the moment.
That means you're connected.
That's what my head is saying as well.
I thought I'd reset this, but clearly not, because it shows 7 connected now. Okay, I'm going to go to the first question here. So the first question is, what kind of bond is it when charged atoms are held together because opposite charges attract? I have well, I am going to stop this and reset it and start again, so you'll have to answer again.
Yeah.
Because it has everybody's answers from last time, which of course were different questions with different correct. And that means that I can't tell. Okay, so go ahead and answer now. One remaining.
Can I change my answer?
I'm not sure.
No, we can't.
Sorry, I did change.
Okay, last person. Okay, well, we'll go with 4. We had 2 people said covalent, 2 people said ionic. The answer is, if you have a charged atom, what do you call a charged atom? A what? We called it an ion.
Okay. Oh, okay.
So yeah, I was still gonna change my answer.
And so the answer is ionic. So Jessica was going to change apparently to ionic.
Yeah, I was
All
gonna
right.
change 2, and then I'm like, nah. It's okay, Jessica, I got you, phones.
Okay, so you all understood that. So if it's held together by charged atoms with opposites attract, it's ionic. Okay, so next case, what kind of bond is it when the atoms are held together? Because they share electrons. We got 4 answers quickly. Guess I'll go on. All 4 of you correctly said covalent. Co means sharing. Valent is those outer electrons. They're sharing outer electrons. Now our third question, how do we differentiate between covalent, polar covalent, and ionic bonds between molecules or between atoms? This was the very last thing from class. Yay. Okay, we had 0, 0, 2, 2, 0. So this one here we're split 50-50 on.
I don't think her answer Frances has been going through. She's been
It's all-
trying.
It's all-
That's why we're confused.
That's what-
with the
okay.
numbers.
So this was the last thing we talked about, and this was one that I thought I would have to remediate. I'm feeling pretty good that we got the idea for the most part. The electronegativity is the key. What is electronegativity? You know, if you just say the electronegativity, you don't know what it means, it doesn't help you out and understand.
All I know is that it's not in noble gases.
It's the periodic table going like this.
Okay, the biggest numbers are the top right, not counting the noble gases.
Yeah.
Smallest numbers are the bottom left. And what they're measuring is how strongly the atoms are trying to attract electrons. It's about the energy associated with adding or removing an electron. So things with high electronegativity like fluorine, they really want to grab another electron. Things with a low electronegativity like francium, they really aren't trying to grab the electrons. They're pretty easy to take one away from. So the keys are, if the difference in electronegativity is greater than 2 between the atoms, then we say, oh, that's ionic. They're not sharing electrons. One of them took the electron, the other one doesn't have it anymore.
Should I write this down?
This is something you'll need to know for the test, yeah.
Okay, so greater than 2.
If it's greater than 2, it's ionic. If it's less than a half, then we say that they're pretty much sharing equally, and thus it's covalent. And notice it's not exactly between 2 and 0.5 is the in-between. From 1.6 to 0.5 is polar covalent, which means they're sharing, but they're not sharing equally. The one with the greater electronegativity is holding more of the electron. The one with less electronegativity is not having as much.
Okay, so what does, oh wait, that's up there on the picture. So polar covalent. I'm thinking out loud, ignore me.
Okay.
It's all good.
Now, what about that region between 2 and 1.6?
That's what I'm wondering.
It can kind of go either way. And now to be truthful and honest, no bond is perfectly ionic, and only bonds between identical atoms are perfectly covalent. Everything is somewhere in between, and so these are just kind of arbitrary cutoff points for what's going on. So make sure you do know those arbitrary cutoff points, but know that in fact all bonds are somewhat a combination unless you have identical things. You know, fluorine and fluorine, that's going to be perfectly covalent. Go ahead.
So with the hydrogen fluoride,
Yes.
hydrogen has 1, right?
1 electron.
And then the fluorine has
7. 7 valence electrons.
okay.
But the key to the bonding is chlorine has a high electronegativity, hydrogen has a low electronegativity. The difference in them is less than 1.6, so it's going to be a polar covalent.
Okay.
I thought you said chlorine says fluorine up there.
Yeah.
Are we gonna have to figure out the electronegativity?
You would have a table with it. You're not going to have to try to calculate what they are for things.
Like it's gonna say what each one is?
Yeah.
Okay, cool.
That was my concern.
Okay, so this here already referred to by Vanessa. We saw it last time. Just a reminder of how the electronegativities vary based on the periodic table. And now talking about polarity. When you have a bond, it's a polar bond if you have one side is hogging the electron. And so if we compare carbon and oxygen, using the standard that we just reviewed, that is things that are on the left have lower electronegativity, things on the right have higher. If you look at the periodic table, oxygen is 2 to the right of carbon. So oxygen has a larger electronegativity. It's pulling the electrons more. So the oxygen is going to have more negative because it's more electronegative. And the carbon then is going to have less negative, which opposite of negative is positive. And so you have both the left and the right sides, as this is pictured, have a net negative charge, and the middle has a positive charge. Now, when I look at this, the charge is still symmetrically distributed because it's a flat molecule. And so it's nonpolar, even though it has two polar bonds, because the charge is distributed symmetrically. So just because you have nonpolar or polar bonds doesn't mean it's going to be a polar molecule. In this case, the picture here is to show what's going on. Remember, it called the electronegativity the pulling power when we looked at this. So these two young ladies are pulling on the rope being the carbon, and these ladies being the oxygen. And if they're pulling with equal strength, neither side is winning, it's nonpolar.
So
now, go ahead.
Anytime is always going to be both right and left will have a negative charge, and the middle will have a positive.
Well, no, that was because of the atoms involved in looking at their electronegativities. Okay. Now, if we go to water, and it's good that you asked that because you would have confirmed that incorrectly by looking at water.
Right. I just want to make sure.
Water, you have oxygen and hydrogen. Oxygen, again, is more electronegative. So the oxygen is negative and the hydrogens are positive. But now oxygen or water is not a flat molecule. Water is bent about 109 degrees between the two hydrogen atoms. So that means it's not symmetric anymore. And if it's not symmetric, if you have one side that has a net negative and one side that has a net positive, then it's polar. So water is a polar molecule. It has a negative side and a positive side. And that's really, really important. Water does some strange things, like water will expand when it freezes. It expands when it freezes because of this nature right here. And if water didn't do that, in the winter when the ponds freeze, the ice crystals would sink to the bottom and the lakes would freeze from the bottom up. Which means that your lakes would actually turn out to freeze solid, because right now the lakes don't freeze solid generally because the ice is an insulator, making it so the stuff below doesn't freeze. But if it's only sank to the bottom, they'd freeze solid. That'd be a very different world. Also, water has a relatively high melting temperature and boiling temperature. I say relatively high. We'll see a table later. But the reason it has those high melting and boiling temperatures is because of the polar molecules. So it's really important to us that water is polar. If it wasn't, there couldn't be life on Earth. It's that simple. So if you have a bunch of water molecules, the negative oxygen is attracted to the positive hydrogen between molecules. So now we're looking at bonds between molecules instead of bonds between atoms. So I have water molecules. The oxygen on one molecule is attracted to the hydrogen on another molecule. And so that keeps the water molecules from just escaping from each other easily. And if you cool it down, it will form a nice uniform structure in ice because of those forces. So I don't have a picture of the ice. I thought I did, but I don't. So we'll move on. Okay, question here. This is actually unrelated to the previous slide, but important, new topic.
I have a question.
Yeah.
Are there tiny little spaces in between these? I don't know, I'm guessing. To make up this?
Yes.
So there are.
Remember, atoms are almost completely empty space. And then molecules are atoms that are bonded together. And so you're mostly completely spaced in molecules. So even though it seems completely solid, it's mostly empty space. Even, you have a chunk of lead, it's mostly empty space. Okay, which molecule is heavier, carbon dioxide or water? We have two answers. Three.
Can you see who's answering?
No.
Oh.
No,
I'm answering in my head.
Vanessa's answering in her head. Here's what we'll do. We'll ask Vanessa to answer out.
Okay, well, I don't know for sure, so I'm just guessing.
Well, it was a tie. So what do you say, Vanessa?
Just say C. You know what? I'm gonna go with C.
It's not C.
Okay.
Darn.
It also doesn't depend.
Does it have to do with where they are on this?
It has to do with where they are on the periodic table. Remember, the periodic table is giving us all kinds of properties. So if we look at hydrogen, hydrogen has an atomic mass number rounded just to one digit of 1. Carbon has an atomic mass number rounded to one digit, 2 units, is 12. Oxygen, 16.
So oxygen is higher.
So oxygen is the highest one up there. And if you want to know the mass of the molecule, you just add them up. So for carbon dioxide, I'm going to take the carbon, 12, plus how many oxygens are in carbon dioxide? 2. So I have to add 2 times 16. So 2 times 16, 32, plus 12 is 44. So carbon dioxide has a molecular mass of 44 atomic mass units, as we call it. Whereas water has 2 H's, so 2 times 1, 2, plus an O, 16. 16 plus 18 is, or excuse me, 16 plus 2 is 18. My brain does that to me. So just to write here the math that we just did, we had the mass of the carbon was 12 atomic mass units. Mass of oxygen was 16 atomic mass units. Mass of hydrogen was 1 atomic mass unit. So CO2 was 12 plus 2 times 16 equals 44 atomic mass units. And H2O was 2 times 1 plus 16 equals 18 atomic mass units. Is that simple enough?
Yeah, just leave it on screen for a second.
Sure. So calculating the mass of a molecule is pretty simple algebra, right? You just take A times X plus B times Y and you add them up. In homework, you'll probably have to do something that has many more molecule or atoms in the molecule.
Is that going to be on the test?
Sure. Yeah.
Okay. Okay.
I mean, everything I talk about in class is potential for the test, but there almost certainly will be something that requires that in the test.
I like your class.
Thank you.
You're welcome. Oh, I love your class. It's just I got only
Answer A, right?
The correct answer is 44, so yes. All right. Next question. Attractions between molecules. What we just saw was dipole-dipole. But that's not the strongest attraction between molecules. The strongest is ion-dipole. So we're putting these in now in order of strength. So this is between molecules, not between atoms. If I have an ion, something that has a charge, and I have a molecule that has a dipole moment, then you're going to have them attract. Because if this thing has a positive side and negative side, and this is positive, the negative side is going to be attracted, pull over, and because it's closer, it's a stronger attractive force of the repulsion between the like charges. So that's ion dipole. The example here shown is what happens when you put salt crystals in water. You know that salt is soluble in water. Salt is one of the things we're going to be looking at in lab. It's soluble in water because water is a polar substance. It's polar, has a positive side and a negative side. And what happens is the oxygens will pull the sodium away, and each oxygen is forming an attraction to that sodium. So the sodium is surrounded by a couple oxygens. Basically, the sodium is a plus charge, and the oxygen sides of hydrogen or of water are fans of that plus. So its fans are clustered around it. Chlorine, likewise, having a negative charge, the hydrogens have positive charge, and they're attracted to the negative chlorine. And so here we're forming molecular bonds between water and sodium and chlorine and water. Those are ion dipole. The ions are the sodium and the chlorine, and then water is the dipole. So that's the strongest of our molecular bonds. Next is, yeah, I was looking at the top one, I'm like, wait a minute, that's the same. Yes, next is dipole-dipole. Dipole-dipole is what we were just looking at with water. It's what makes water hold together, makes water have an elevated boiling and freezing temperature because of the dipole-dipole bonds. So this is showing the negative side of a water molecule forming a dipole-dipole attraction, which we call a hydrogen bond in this case, with the hydrogen of another molecule.
Can you give me, sorry, and you guys probably don't know this, but what is a dipole?
Okay, dipole is when we have charge not symmetrically distributed. So one side is positive and one side is negative. So di means two poles is charge polarity.
So when we have a charge that isn't specifically positive or negative.
That's an ion if it's specifically positive or negative. A dipole is neutral, but the charge is not symmetric. So one side of it will be positive, the other side will be negative. But the entire thing is neutral.
Thank you.
Now the next one is one that you have, actually almost what you have experience with. With the balloons. We made the balloons charged. This isn't one of the answers here for the bonds, but we made the balloons charged, right, by rubbing them on our hair. And then I was able to stick this to the, definitely sticking to my hair, huh? Able to stick to the wall. Why was I able to stick to the wall?
Because you gave it different charges, like rather forcefully.
What happens with, go ahead.
It moved the charge.
It moved the charges. I had my balloon, and you drew a picture of this. See, it's the rubber, so it's negative. So there's the balloon that has negative charge. It took electrons from my hair. And then we bring it up to the wall. And the wall is neutral, but that negative charge there is going to push away electrons in the wall. So it's going to make it so the electrons move away, leaving this side positive. This here is an induced dipole. Dipole because the charge is separated. Induced because the wall wasn't a dipole. But when we brought that charged object there, it induced it. Now the dipole-induced dipole is the same idea, except for instead of bringing a charged object up, that'd be an ion, we're bringing up something that has a dipole moment like water. So water having a dipole moment, if it comes close to something like hydrogen, that's H2, it can make the charge of the hydrogen shift, and then when it shifts, it's a dipole, and then you're going to have an attraction. So here is an example, an oxygen molecule, two oxygens bonded together. It's perfectly nonpolar because they're the same molecule. But then if I bring it close to a water molecule with its dipole moment, since this side here is negative, then it's going to push the negative and the oxygen away, leaving the other side positive, and then you have an attraction. So that's the number 3 on our strength, going down in strength. So the strongest was ion dipole. Next was dipole-dipole. Now we have dipole-induced dipole. We have one more. This last one is really weak. And the last one is induced dipole. That is, you take two things that are nonpolar. So let's say, for instance, I bring 2 helium atoms together. Each helium atom is neutral. But they have electron clouds on the outside and positive nuclei. So they have electrons all around the outside. If I bring them together, the electrons from one are going to repel the electrons from the other, and you can induce a small dipole moment. And then that induced dipole moment can make it attracted to the first one. As you can imagine, this is really weak, because you have to force them together to make them induce a dipole, and then have that weak force holding them together. So I use helium as my example. You'll see the example here is argon. What do helium and argon have in common?
They're both positive.
They're in the same group. They're both noble gases. They're both things that we say are chemically inert. They don't form bonds, and yet you can get this very weak induced dipole bond between them. So this is an example. Now, something that's way beyond this class. Liquid helium, you can make it into a super fluid, and the reason you make it into super fluid is these kinds of bonds forming. All right, I think this is just.
Can you go back for like 1 second?
Yeah, there really was nothing important on that slide.
Okay, we're good.
This is then showing what we've just gone over from strongest to weakest for the intermolecular, the forces between, the bonds between molecules. So make sure you know this order, and you can identify what makes it an ion dipole or a dipole-dipole or a dipole-induced dipole. The dipole-induced dipole is the one that I think is the most confusing. You have to think about it the most. Any questions about these bonds between molecules? All right then. Here is an outcome of these kinds of intermolecular bonds, the bonds between molecules. If you have polar molecules, so HF was an example we saw of polar, water is polar, ammonia, polar. These polar things have boiling temperatures that are in the range of our everyday experience. -33, yeah, I get some -33 here. 100.
Celsius.
Yeah, they're Celsius.
Okay.
100 Celsius, well, no, it doesn't get to 100 Celsius, does it? That'd be 212 Fahrenheit. But these are in the ballpark of everyday temperatures. We boil water at 100 degrees Celsius all the time. So water, ammonia, hydrogen, fluoride, they all have boiling temperatures that are everyday type temperatures. But if you go to nonpolar molecules like hydrogen, oxygen, nitrogen, these are all nonpolar because they're perfectly symmetric. Boron trifluoride, that you think, well, free, how is that? Well, they're just spread out in a uniform arrangement. Or carbon dioxide, we saw it's flat. Because these have nonpolar structures, instead of having dipole-dipole bonds, you have to have induced dipole bonds. Much weaker and hence much lower melting temperatures.
Wait, so
or boiling temperatures in this case.
So the colder it is, the more likely they are to boil?
No, what it's saying is these are not held together very strong at all. So they can boil completely separate at very low temperatures. These, because they're polar, they have dipole-dipole forces, and you have to have a much higher temperature. That is, they have to be banging around much harder to break apart. So there's a very clear outcome of the difference between polar and nonpolar, giving us dipole-dipole versus induced dipole bonds. Okay, another clicker question. We're shifting each clicker question. Well, the last clicker question brought up a new topic. This is bringing up another new topic. Is it possible for a fish to drown? Anybody here own fish?
I can't.
Not anymore.
Can't keep them alive?
Oh, no. It's not. I know with sharks, like if they're not moving, they don't have fins and they can't get the oxygen levels. Doesn't say that.
Okay, given that Vanessa is not able to get her answers in, I believe everyone has answered. This, when I was a kid, this was a totally legit question. I was like, how can a fish drown? The answer is yes, they can drown. How? You may see aquariums. And what do they have in aquariums?
They have the little filters.
They have little filters. That's important because you don't want the water to be all gunky. But they have also either plants or little bubblers. And that's because the fish don't breathe water. I mean, they do, in essence, that is they have their gills and they bring in water. And then they filter oxygen out of that water, but they're not separating water molecules to get the oxygen. They're taking oxygen that is little air bubbles in the water. And so, of course, if there's little air bubbles in the water, the fish can live. If there's no air bubbles, they don't. So how do you get those air bubbles? The reason they have little bubblers is to make air bubbles in the water, to aerate it, so then the fish can take that oxygen. Or the plants, as you know, plants take, well, we say carbon dioxide, and then they produce oxygen, right? And so they produce little bubbles of oxygen on the plants that then the fish can breathe. So even though water is 88.8% oxygen by mass, how do I get that 88.8%? Well, we determined that the mass of water was 18 atomic mass units, and the mass of oxygen is 16 atomic mass units, so just 16 over 18 is how I get that number. Now, the bottom one, yes, when the water is not moving. That actually is a reasonable answer if anyone, well, one person did say that. That's a reasonable answer because when the water is moving, you generally allow it to aerate. So a stream with water going over the rocks, you're going to form air bubbles when the water is going through that turbulence over the rocks, and it aerates the water. And so that makes it so it's something that a fish can live in. So if you have a pond, still water, and no plants, the fish can't live because there's no oxygen. Even if you put in stuff they could eat, I don't know what they could eat that's not a plant, but that.
So what's the correct answer?
So the correct answers, that's the fundamentally correct one, but this one here plays into that. All right. Just a couple more things on the intermolecular. Well, we only have 2 minutes left, so yeah, we'll finish this section, but we won't start the next one. Teflon. Anyone here a fan of Teflon? No.
What?
Anyone an anti-fan of Teflon?
Anyone had Teflon?
Well, we usually have Teflon-coated pans.
Oh, it's a coating. It's not
Yeah.
a food.
Right, it's not a food. It's not a food.
Well, there's an omelet right there. So like,
Yes, but it's the pan that we're interested in.
I mean, I'm not
Amy is anti-Teflon, just for the record, because it's got these floorings.
So yes, then is it in almost any nonstick pan?
Yes.
Then yes, I've been with Teflon.
Okay. You can also get ceramic, fairly nonstick. But the reason fluorine works for nonstick pans is because you have, here's the basic unit, carbon with the fluorine on each side and carbon going out each direction. It's nonpolar because it's symmetric. And so you have nonpolar molecules. Nonpolar molecules don't bond much with other things. Right? The only way they would have is the induced dipole idea. And these aren't going to induce much dipole because the fluorine-chlorine bond is highly polar. So it's pretty much an inert substance. And as I understand it, you can eat Teflon because it's inert. It'll just go through you, just like eating a rock will. But it's because of that nonpolar molecule that Teflon then is a nonstick material. Last thing, gecko's feet. How do gecko's feet stay so clean?
They're naturally coating Teflon.
Well, no, not exactly. I think I already asked. No, I didn't ask you that. Well, we're out of time. The bottom one, yes, induced dipole, induced dipole.
Go, Vanessa.
The gecko is actually really interesting in how its feet stick, but we clearly don't have time to talk about that. So I'll see y'all for lab tomorrow. Make sure you work on that flow diagram for how you're going to do your tests, because that will make life much quicker for you in lab.